you to the next slide for a second. What we did here is use switchgrass as generation 2 cellulosic biofuel. We took out all the energy that was required to process it, so this could be done in a sustainable way. We took out the waste heat that comes from an internal combustion engine and said, let's run one car for 30 miles a day, which is the average for the U.S. And we worked back and we found that we need about 0.6 hectares of land to be able to run, one car. Well, then we said, okay, let's see what the possibility is of doing this in a sustainable, zero carbon emissions way. To do that, we took commercially available solar cell technology, that's available today. We did the same kind of analysis. We said, let's take the energy that is required to build, to manufacture the solar cells. Let's take that out, take it into the grid, take out all the waste energy that occurs in an electric vehicle, and then we try to see how many cars could be operated with the same land base that we have. And the answer was very surprising. We came out with about 331 cars. So this is telling us that there's a very significant difference between what the resource use is for a electric car versus a car that is powered by biofuels. And what this tells us is that as you scale the biofuel use, you have to worry about what the resource limits are going to be in terms of land use and water use. And it also appears that for this market segment, at least, electricity might offer a viable alternative. It doesn't mean that biofuels cannot fill this void, but our feeling is that you need to get about a 50x improvement in resource utilization efficacy if you're going to be able to to use this technology at global scale. Well, okay, fine. Let's go to one more use for petroleum, and which is really as organic feedstock, and the entire plastics industry, all of those. And this is a possible market for biofuels. But when we look at biofuel scalability, it looks as if 20 to 30% is the number that most people are comfortable with in terms of what biofuels can scale to. And if we look at this percentage usage here, that's about 20%. So it almost looks as if biofuels might be a really good fit for this middle band. The lower band actually can continue to be used from petroleum because really there are no emissions associated with it. And in the near term, this is an easy way to fill that. So okay, so we've addressed a couple of things out here. We said that maybe target biofuels out here, and maybe target petroleum out here, and maybe look at electrification and in the light auto segment. Well, we kind of also did a little bit more in terms of scaling, and we tried to look at the U.S. transit scenario, and we compared 4 scenarios here. 2 are sustainable, and 2 are kind of based on fossil fuels. Okay, so the first one here is business as usual, which is internal combustion engines, and this is handling the U.S. transit requirements. We have 4 quadrants out here. We have 4 quadrants out here. One kind of looks at resource use. One looks at security, which is petroleum imports. One looks at emissions, which is greenhouse gas emissions, and one looks at energy, and how much wasted heat is generated. And the baseline is really business as usual. Then we looked at, okay, what happens if we move to biofuels? If we move this to biofuels, and we run them sustainably as we had shown before, you find that your petroleum imports go to 0, and your greenhouse emissions go down, which is really, very desirable. But you see what happens to your land utilization. What you find is you take your amount of land for food, and you take the amount of land for transportation, and you've pretty much got 70% plus of U.S. land mass being used. So from a scaling perspective, this really would have a very difficult time scaling to 100% of transportation needs. Well, we've seen a lot of advertisements that talk about electric vehicles as being zero emission. Okay, well, let's take that in context and take existing generation as being the source of powering the electric vehicles. And what we now see is that compared to the internal combustion engine case, you see emissions go down by about 16%. Petroleum imports go away, and so that's, from a security perspective, this is very good. Land and food, food is still 20%, and land is essentially zero requirement, and waste heap is managed. So this looks, reasonably attractive compared to the business as usual case, and certainly from a land utilization looks better than biofuels. On the other hand, now if we could think of some way, and I don't know how we do it, but if you could think of a way to power transportation from renewable energy such as solar or wind, okay, has no carbon emissions involved in that whole process and the whole chain, okay, how would we do that? Well, this turns out to be really very interesting from a resource perspective because A, you have no imports, so security is very good. You have no emissions, so emissions very good. And lo and behold, the efficiency of the solar land utilization gives you an advantage in terms of how much land is required to support, transportation in the U.S. and waste, waste heat also goes up. So, overall, just, forget dollars, forget everything else. Just look at it from a resource perspective and security perspective. It certainly looks as if PV is very interesting and attractive. Frank and I did a paper in the IEEE Spectrum magazine late last year, and what this does is trying to scales this to a global level. Because, if you show that biofuels are very attractive in terms of price, why wouldn't everybody use it? If biofuels are attractive in terms of price, why wouldn't you use it for electricity generation and for, organic feedstock and everything else? So we looked at 4 scenarios here where we looked at business as usual. We looked at an inorganic world where all the power is derived from solar and wind. And we looked at the biofuel world where all the energy is derived from generation 2 and 3 biofuels. And we, kind of boiled it down to say how much land is required, how much water is required, and what the emissions are. And your baseline says 2% land required for supporting energy and food, 5% for, for supporting energy and food of water, and 17 billion gigatons of, or tons of carbon emissions. If you look at the biofuel world, you need 193% of the land and 173% of the water. So this is an absurd case. We just want to show that as you start scaling it up, you're going to start seeing some pressure on resources. What was surprising for us was that in terms of energy requirements, the inorganic world supported by photovoltaics, was actually very sustainable in terms of land, in terms of water, and in terms of carbon emissions. And we now have a website that's called www.inorganicenergy.com, and if somebody is interested, they can go and create their own world and look at the energy mix and look at the emissions and look at everything else that comes from that. So, you're welcome to do that and send some information back to us. The model that is there on the website we've used now to kind of look at various scenarios, and we've looked at business as usual 2006, 2030, biofuel world, and inorganic energy world. And what this does is kind of gives you the total requirements in terms of land, in terms of fresh water, in terms of fossil energy, waste energy, carbon, food. And just something to kind of point out here is the prosperity level. We took the U.S. 2006 prosperity as 100% prosperity level, and then we kind of looked and said, what should resource availability be in 2030? Clearly Africa and Asia and everybody else may not get to 100% of U.S. 2006 levels, but we said that you have to assure at least resource availability for them to be able to get to that. We call it an aspirational prosperity level. And if you do that, that's the resource that you have to provide for. And once again, I mean, this model is available. And all the assumptions are kind of there, and if there are questions, we'd be happy to talk about that.